Today, we are getting under the skin of one of the most advanced machines ever built, the F-35 Lightning II. Now, this isn't just a fighter jet. It's really a testament to what happens when engineering precision gets pushed to the absolute edge of what we think is possible.
And that brings us to a huge question, one that the engineers behind this aircraft had to face every single day. How do you actually build something that, on paper, looks pretty much impossible? Well, that's the journey we're about to go on.
Okay, so let's get into it. The core challenge here, the big idea behind the F-35, wasn't just to build one great jet. No, it was to build a single aircraft platform that could pull off three completely different, incredibly high-stakes jobs for the Air Force, the Marines, and the Navy.
First up, you've got the F-35A. This is the Air Force's workhorse. Think of it as the foundational model, your classic air superiority fighter built for regular, conventional runways. To stay stealthy, all its weapons are tucked away inside internal bays. And it gives its pilot this incredible view of the battlefield through something called sensor fusion. Basically, the jet's brain takes data from all its sensors and merges it into one simple, clear picture. Oh, and it can hit Mach 1.6 without breaking a sweat.
Now this is where things get kinda wild. This is the F-35B, the one built for the Marine Corps. You know, this thing is less of an airplane and more of a physics masterpiece. So to take off and land vertically, it uses this giant lift fan in the front and a rear engine nozzle that actually rotates downwards. The real magic, though, is how the onboard computers manage the airflow and thrust between those two things in milliseconds to keep it perfectly stable. It literally defies gravity.
And then we have the F-35C, the Navy's powerhouse. This version is engineered to survive the unbelievably brutal world of an aircraft carrier. You'll notice it has the biggest wings of the three. That's absolutely critical for generating enough lift to land at the slower speeds you need on a carrier deck. And the whole frame, especially the landing gear, is seriously beefed up to handle what is basically a controlled crash, over and over again.
So, you've got three incredible, distinct jets that all come from one core design. But that just tells us what they can do. The far more interesting question, I think, is how. What's the actual science and engineering going on under the hood that makes any of this possible?
All right, this is where we get to the heart of it all. We're going to break down the three big principles, lift, thrust, and stress, that allow the F-35 not just to fly, but to totally dominate the sky.
Everything, and I mean everything, starts with the most fundamental concept of flight, lift. It's that invisible force that shoves the plane upwards, fighting gravity every second. The simple version is that the air moving over the curved top of the wing travels faster, creating lower pressure, while the air underneath is slower and has higher pressure. That difference is what generates the upward force.
Now, engineers don't just guess at this. They calculate it with extreme precision, and this is the magic formula they use, the lift equation. L is the lift we're trying to find, and it's based on rho, that's just the density of the air, times v squared, the velocity, which is super important. Then you've got CL, a number based on the wing shape, and S, the surface area of the wing. You mess with any one of those, and the whole result changes.
So let's plug in some real numbers. Let's say we have an F-35 on its final landing approach going about 80 meters per second. When you run the math, you get a lift force of roughly 161,000 newtons. But okay, what does that number even mean in the real world?
It means the wings are generating enough force to lift about 16 tons. Let that sink in for a second. That's the power of aerodynamics right there. A machine that weighs tens of thousands of pounds is literally being held in the sky just by carefully managing how air flows over its wings. It's incredible.
But lift is only half the battle. You also need that forward push from the engine. You need thrust. And this is where things get really cool. Take a look at these numbers. The engine can kick out about 191 kilonewtons of thrust. The aircraft's weight, right around 190 kilonewtons. They are almost identical.
What that gives you is a thrust-to-weight ratio of nearly 1-to-1. And folks, that is the secret sauce. That's what lets this jet accelerate like an absolute rocket, climb straight up, and in the case of the B model, literally push itself off the ground into a hover.
So, okay, we've got an insane amount of lift and unbelievable thrust, but this creates a whole new engineering nightmare. Can the actual physical structure of the plane, the airframe, survive the mind-bending forces it's creating?
And once again, engineers have a formula for that. The math for stress is actually pretty simple. It's just the force on a part divided by the cross-sectional area of that part. This tells them exactly how much strain the material itself is under.
Now get this. During a really aggressive high-G turn, a single structural part might have to deal with a stress of 400 megapascals. That is a ridiculous amount of force concentrated on a tiny area. Your standard aluminum or steel? Yeah, that would just snap.
So, the solution isn't just about clever design. It's about what the thing is made of. The F-35 is built using this exotic cocktail of advanced materials. You have titanium alloys that give you the strength of steel without the weight. And then you have carbon fiber composites, which are incredibly rigid and have the added bonus of absorbing radar signals, which is key to its stealthy shape.
But there is one final brutal extreme we have to cover. A challenge that really pushes materials science to its limit. And that's surviving the unbelievable heat that pours out of that powerful engine.
And just look at the scale of this problem. The engine exhaust can hit 1700 degrees Celsius. That is hotter than lava. But the advanced titanium in the frame starts to weaken and fail at around 550 degrees. So how on earth do you keep the jet from literally melting itself from the inside out? Well, the answer is a brilliant multi-layered defense system. The parts closest to the engine are made from special high-temperature composites. Then those are coated with ceramics that act like a mirror, reflecting a ton of that heat away. And finally, you have layers of advanced heat shielding that insulate the rest of the plane, keeping all the critical electronics and structures safe.
So next time you hear a description like this, you'll know what's really going on behind the words. Advanced aerodynamics isn't just a marketing term. It's the 16 tons of lift we calculated. It's the synthesis of all these amazing technologies working together perfectly.
Because in the end, the F-35 isn't just a collection of cool parts. It's a perfectly balanced symphony of extremes: extreme power, extreme stress, extreme heat, all managed by extreme engineering where every single choice works in perfect concert to do the impossible.
And that leaves us with one last thought to chew on. The F-35 represents the absolute cutting edge of what's possible with engineering today. So the real question is, if this is what we can do now, what in the world is the next generation of aircraft going to look like?